Good morning, everybody, and welcome to physics. We are in week 6. There is something going on actually that I am debating at this point, so I really wanted to start with it, and that is concerning exam 2. Exam 2 is planned for week 8, which is not next week, the week after. So that is the original plan that we have. It's probably, it's still not a decision yet, so it's still something I'm debating. Hold on, guys, I need to sorry about the noise. Anyway, I had to close the window. Anyway, the point being is that it looks like we may, okay, and probably now I'm working on it to see how it's going to work, and that the exam 2 is going to be held on week 9, meaning that we're going to cover a little bit more material for it. But the point in here is that we're going to push it to week 9. Okay, so that's the idea for it. That's the thing that I have in mind, and it's probably, if we're going to do it again, it's going to be on a Wednesday, or either week 8 or week 9. So that's again the plan. I usually don't like to do exams in the middle of at the beginning of the week. I like them actually to be in the middle of the week, so that to overcome any kind of problem. So that's really what the idea for that exam is. So next week there is no exam. It was never planned, and it's not going to be. So week 7 is not part as an option, but it's rather week 8 or week 9, which gives you more time to review the problems that we did yesterday in the lab session. I know we went through a lot of problems that we discussed in there. As a matter of fact, we did in detail 11 problems yesterday, and I followed up with a message. There were 2 or 3 people who were not in attendance yesterday, that this is what we did, and they're still also responsible for all of the content that we did there. But you have actually more problems that we shared together, and they're actually posted also on Canvas, namely on this week's lab session, because the lab was not, we didn't really have a lab like we normally do, in the sense we have an activity and so on and so forth. It was all dedicated to problems, and we solved at least in detail 11 problems, and those are still an ongoing thing that is going to be needed for the exam. There will be at least another homework that is going to be assigned next week that is also going to be included as part of the exam, so that you guys are aware of it. And we may dedicate, actually, that's why actually I'm thinking to postpone the exam, because there is more content coming down the road, as we may dedicate part of this lab sessions just to go through some of those problems from the next homework set, which is going to be assigned next week. So, which is also going to be part of exam 2. So that's really the idea behind all of this, basically adjustments, so that we will accommodate for everything, and we will be ready 100% for the exam time. As I said before, exam 2 is slightly different than exam 1 in the sense that it's not only conceptual, but also you have a problem section of it. You have a component on it where you're going to be solving problems. And those are going to be 2 distinct exams, okay? There will be an exam for the conceptual that you're going to be prepared the way that we prepared the exam 1. And you're going to have the allotted time for it again, similar to exam 1. And there will be another one, usually either the day before or the day after, just dedicated to the problem solving section. And there is a ratio with the 2 that are going to be added to be considered as your total grade for exam 2. So it's not that you're going to have a separate exam. It's not like you're going to have exam 2 and exam 3 separately. No, they're going to be considered only one exam. So this is something that I wanted to share with you guys, so that we're at least aware of what's happening and what's going on. In terms of content this week, it's a continuation of what we started actually on Monday, and that is the topic is still, let me share the screen first. Share. My OneNote. Okay, so we're still ongoing with the topic that we started last time, and namely the biggest thing is that we're doing motion in 2D. Actually, it's a multi-dimensional motion in general. A 2D, the case that we did last time was the circular. That's my pen. Oh no, it's not that drawing. That's why. So the circular motion. Circular motion is a special case of a multi-dimensional motion. It happened to be a 2-dimensional motion. okay? Circular motion, if you guys remember, anytime I have a center and I have an object going around a circle. So a circle, if you guys remember from your geometry class, is the collection of points that are at the same distance from another point. Okay, that doesn't belong to the same circle. So all of these points have the same distance, and that distance by definition is a radius. So the collection of points, the word in geometry is equidistant. Equidistant, meaning they have the same distance. Equidistance from another point. And that point is actually a center now. So there is a terminology used in circles. So this is now a center, and this is by definition a radius. That is that distance that we're talking about. So that is basically what the circular motion is. A special case of the circular motion, if you guys remember, I have two kinds of accelerations. I have two ways of going around this circle, either by having this velocity increase in magnitude or decrease in magnitude, doesn't matter. It was, let's say, 5 meters per second, now it's 4 meters per second, then 3 meters per second. As long as it can change one way or the other. If it was 1, then it's 2, then it's 3. So while I'm going around the circle, I could have a velocity increase in magnitude. That is represented by the tangential acceleration, or the acceleration along the tangent. In addition to that, I have another acceleration always, no matter how the motion is being described, namely the centripetal acceleration. The combination of these two accelerations, it's a vector sum of these two components, will give me what I call the acceleration. In the case when the tangential acceleration is 0, this is a special case of interest, which is the uniform circular motion. Meaning circular motion, meaning it's moving without either gaining or losing speed, but going around the circle. So the velocity is changing. So the speed does not change. That's what the tangential acceleration does. It changes the speed in this case. But the centripetal acceleration is always never 0. Cannot be 0. In a circular motion. As a matter of fact, we gave it the expression for it because we found out that the centripetal acceleration is going by the square of the velocity divided by that radius. The radius cannot be infinite. I mean, if it's an infinite radius, that means you're going on a line. In that case, yeah, since there is no acceleration, no tangential acceleration, and no centripetal acceleration, that means the motion is actually on a line and it's never going to turn. Hence the centripetal acceleration is 0. And it's not changing in magnitude, meaning I'm not gaining speed or losing speed, so I have the same speed all the way through. So that means actually the tangential acceleration is 0 too. So this case encompasses all situations, but in our particular case, the radius is finite. So I'm dividing by a radius and I'm squaring the velocity. Remember, the velocity must be a quantity, because if the velocity is 0, that means, hey, the object is not moving at all. So I don't have motion to begin with. So if the velocity happened to be also 0, so it doesn't make sense to talk about acceleration or centripetal or tangential, because they don't have even motion at all. So no motion. And I know I said before that the word motion is equivalent to speed, actually. If you have the speed, you have motion. If you don't have speed, you don't have motion. So if somebody asks you what is motion, it's basically the fact that whether or not you have motion, or you have speed or not. So that is the telltale sign of what motion is. So this is what we did up to this point, and we discussed this extensively. So this is a two-dimensional motion, which is a special case of a multi-dimensional motion. I mean, in terms of the dynamics, there must be a force to retain this object in orbit, because if for some reason this object is cut from that center, it's not going to go in a circular motion. So what I have in here, I have a mass. Actually, this is part of another experiment that I used to do. for electricity, and we probably are going to do that. So I have a mass suspended by string. Now, if I spin the string in here, it's going to go in a circular motion. And what keeps it, the center of the circular motion is somewhere in here, okay? It's not in where my finger is hanging. It's really near to where this thing is orbiting. So it's a circular motion, and the radius is the distance that is this one. So that is a circular motion. And something is holding it in this circular motion, because if I come in here and cut it with the scissors, what happened? It's not going to continue the circular motion. It's going to fly away from the point of release. So it's a very important point in here to remember that there is a force in here that causes this to stay in circular orbit. So if I have, for example, a planet going around the star, then there must be a force, and that force is exactly the force of gravity in that case. So for the case of a star like the sun and a planet like the Earth, then hey, the force of gravity will supply that force. It's like a string holding the planet attached to the star, except that this force acts at a distance. That's all. So this is a force that acts at a distance. That's actually the next topic of the next chapter. Okay, force that acts at a distance. In other words, you don't need a string. You don't need to attach yourself to it. So you need a force to bring it to that to maintain it in that orbit, similar to the string I was demonstrating earlier with this mass. Now, we found what that force is. Actually, it's not hard to find it. It's the mass of the object that is orbiting. We don't care about the center in here. It could be just like, for example, I was holding it with my finger. It could be just any point, mathematical point. But what matters is the mass of the object that is spinning, this object, okay? That matters, okay? So it's that mass times the acceleration. And what acceleration we're talking about? We're talking about the centripetal acceleration, AC. So it's mass of the object times AC. Remember, the force is a vector. And the acceleration also is a vector. Both of them are vectors. So which way they point? They point toward the center. The force and the acceleration point towards the center. Hence the name, centripetal. Hence the name. Centripetal acceleration. I know I mentioned last time centrifugal acceleration, and that is actually inertia. That's a force of inertia. If I do this experiment again and let it spin for a while and then come and cut it, what happened is going to fly away due to the force of the centrifugal force, which is really an inertia. An object wants to maintain its state of motion. So in other words, this is the scenario I was talking about. Let's say, for example, I have actually an object that is attached via string, actually, like the experiment I was describing, and it's going in a circle around the center of rotation. Okay? If I come at some point and cut the string, this object will, because remember, the velocity is always tangent to the path. At any point in here, the velocity is always tangent to the path. So if I cut it in here, it's going to fly in this direction of the velocity where it was going. And it's going to stay there because of the first law of Newton. So if after a while I cut it, the string now is loose in here, and the object will fly attached to probably the portion that is in the same direction as it was going in the beginning, with the same velocity, okay? So now this is a snap, and the string has basically come up, and the center is here. So now the object will continue in this direction forever and ever and ever, as long as there is no external force. Of course, if there is air, it's going to slow down. If the force of gravity is going to cause it to fall down, and so on and so forth. Okay, so that's the idea behind it, and that is the centrifugal force. So that is, again, when you do F equals to ma, it's the ma part of it. Okay, that is just the centrifugal force is an inertial force. Centrifugal force is an inertial force, meaning it's not real force. Okay, it's not a force due to interaction of two objects, like the force of gravity. The force of gravity, two objects are actually acting with one another. The Earth, for example, on Earth, and the body that you have in there. Okay, so that is actually two systems interacting. That's what we talk about when we talk about real forces versus these things which are called virtual forces. Anyway, this is basically what we covered last time. So let me build on that and tackle the projectile. I know we did a problem, and that's problem 66 from page 77. Page 77, problem 66. Sorry. Backward. Okay, so that problem is actually a very good problem to revisit again, and hopefully we will going to gain some insights from it too. Okay, so the problem, if you guys remember, says that you have an object, I don't know what it was named, the problem, that was initially given an initial velocity going 6 meters per second on the x-axis and 30 meters per second going on the vertical axis. So this is a big number, relatively speaking. This is 5 times as big as the other one. So on the x-axis, it was given a much bigger velocity than on the y-axis. So the object obviously was thrown for practically, for the most part, in the vertical direction. Because remember, if I want to add these two vectors, I draw from the head of the second one, the tail of the first one. So I'm going to draw, add to it this vector 30 in the vertical direction plus 6 in the x direction. I have to go, for example, to the 6 and add the 30 here. And now I draw from the tail to the head. This is the actual direction of the, I think it was a baseball, of the baseball when it was hit. Okay. So that is basically, so what this length is 30 meter per second, and this one is 6 meters per second still, and that's the direction I've thrown. Of course, it's the same sum as if I add 30 plus the other 6 on the other side too, when I go to the tail of, to the head of the 30 and draw the tail of the 6, but it has to be parallel to it. It's going to result in the same vector. This we saw it when we did vector additions lab and so on and so forth. So the point being in here is the ball for the most part was thrown in the vertical direction. We were asked actually 2 questions, okay? We were asked how long this object will stay in flight. We were asked also how far it's going to venture in the horizontal direction, okay? Now we can answer both questions. And we did it actually part of the exercise. So it's a good thing to come back to. There is another question that we could ask. So the first question is the time of flight. The second one is the range. Basically, how far it's going to go. That is what the range is. And we could have asked the question, how high it's going to fly? How high, what's the highest point in here? Highest point. That is really the question. We could ask that too, okay? Would we be able to hit something that is flying, for example, above us? That's something that we are interested in. So those are some of the typical questions that we could ask and try to answer in this scenario. I know we did the first 2 in the lab, I mean, in part of the lab when we were doing problem discussions. And there are many ways of doing this. We could go all math on it, but we could simply make the following argument. Remember, there is always the force of gravity in the case of the projectile. So we're doing the projectile right now. We're going to go to the second part. Where is my pen? There it is. So in the case of the projectile, you will always deal with G. G is always pointing toward the Earth, and it's always 10 meters per second squared, meaning an object that is falling is going to gain more speed than what it already has for every second, 10 meters per second, in addition to what it had. And an object that is going upward, because this gravity, the acceleration is pointing down, will lose actually this much speed for every second while it's climbing up. So that's really the bottom line, okay? So G in here, object moving down gains an additional, whatever it had before, it's going to have more, an additional 10 meters per second for every second thereafter. Now, an object that is going up will do the opposite. An object moving up, an object moving up loses 10 meters per second. So once we have that, we're in business. So let's switch back so that we can see what's going on in here. So again, so here is the scenario. Initially, the object was moving in the vertical direction. Let's focus just on the vertical for a moment, okay? With 30 meters per second. Okay, so that's the initial speed. I know we wrote the position, the displacement in the vertical direction as being, in this case, because the gravity is negative, is pulling it down, as being negative 1/2 of g times the time square plus the initial velocity. In this case, it's 30 meters per second, by the way. So that is the initial velocity, 30 meters per second times the time. So initially, the object has no displacement. It was still here. So D stands for the displacement in here. After 1 second, where is it going to be after 1 second? Well, this is 30 times 1 second. This is negative 1/2 times 10, and this is 1 squared. So negative 1/2 times 10, that is -5. 1 times 1 is 1, so this is -5. Plus 30 times 1, that's 30. So it's going to be 25 meters above the ground. It's going to be 25 meters above the ground. And let me draw that this is where the 25 meters above the ground is. So after 1 second, the object will find itself 25 meters above the ground. But how fast it's moving? Remember, it's moving up. So it's going to lose 10 meters per second. So it's no longer 30 meters per second, but rather now it's just 20 meters per second. So this is how fast it's moving, 20 meters per second. Okay. Remember, this vector is here, not here. Same thing with this vector, 30 meters per second is not here. It's in here. This is where it's affecting. So the starting points. So this is 1 second of flight. This is what happened to it. It's at a height of 25 meters, and now it's at moving slower, plus 10 meters per second in that 1 second. Now, after another second, so this is after the first second. Now, after the second second, the object is at a distance -1/2 times 10 times 2 times 2, which is 2 squared, plus, in this case, 30 times 2. So let's see what's going on in here with the math to help us. -1/2 times 10, that's -5. 2 times 2, that's 4. And then 30 times 2, that's 60. Well, -5 times 4, that's -20. Plus 60, that's 40 meters. So the second time around, it throws not 25 in addition to the initial one, but it throws only 20 meters. In addition, no, I'm sorry, it throws what? How many? To 60, it throws 35 more meters. I'm sorry. To get to 40? No, 15. I'm sorry. It's here. It's at 40. It's at 40 meters. Okay. So remember, we started somewhere, and I'm not drawing it to scale, so it's not going to be probably accurate. I probably should get the grid and start counting how many. I mean, there is a feature in here where you could get grid. What is it? Okay, view maybe. Yeah, I could have gotten some of the rule this grid in here, and start working with it. But hopefully it's good enough, I mean, to understand. If you have rulers, you could really get this thing more accurately. So the point being in here is we are at 40 meters after 2 seconds. And the speed now, we lost another 10 meters per second in that second. So the object now is moving slower. This is its speed now. It's 10 meters per second after the second. Okay. How far is this going to be from the ground? Well, it's going to be after the third second now. So now we are the third second. So this first and second and the third are just the seconds that are ticking. So every one of this, another second ticks. So the object now is going to be at a distance of negative, again, 1/2 times 10 times t squared plus the initial velocity times the time. And the time in this case is 3 seconds. So it's going to be the distance now, the displacement is going to be negative 1/2 times 10, that's negative 5, times t, which is 3 now. 3 times 3, that's 9, plus the initial speed, which is 30, times 3. So now the object is going to be at a distance of negative 5 times 9, that's 45, negative 45. 30 times 3, that's 90. And the object would have moved 45 meters from the start. So remember, it was in the origin here, it went 25 meters after the first second. The second only went another 15 meters to 40 meters. And now it just barely made another 5 meters because it's moving a lot slower now. So after the third second, the object has reached a height of 45 meters. And now, what is its speed? In the next third second, it's going to lose another 10 meters per second, but it's already was moving at 10 meters per second. So if you deduct from it 10 meters per second, the object is not moving at all. So the velocity at the end is 0 at this point. So it stops, really. So at this point, after the third second. So this is what's going on when the object was going up, okay? I could do the same analysis and argue that the object now is going to fall down in the similar fashion. And that's exactly what we did in the lab, so that now, except we didn't take account of the distance. Now we know how high it's going to go. This is the highest it's going to go, 45 meters with this initial speed. But it's going to come down ever since from that point. It's not going to continue climbing. So it's going to gain 10 meters per second. And now on the way down, from this point in here, is going to be moving at 10 meters per second after that initial gain. So, and then after that, it's going after the third second, this is actually the fourth second. And this is the fifth second. It's going to be moving at 20 meters per second, opposite to just this number, whatever it was in here, okay? And so this number in here, by the way, this is 20 meters. Here is 20 meters. It's in this number, not here, okay? Same thing. This 20 meters per second is not pointing in here. It's actually here, where the fifth second is. And then after the sixth second, it's going to be moving 30 meters per second down. And that is the sixth second. So we answered in the lab, and we were correct to say that the entire time flight was 6 seconds. 3 seconds to go up and 3 seconds to come down, okay? But what we didn't do in the lab, if you guys remember, that was not a question that was asked actually, but it's now we know it's not hard to really do. All you have to do is try to do this math. But the point being in here is it gives you an idea of the entire picture now, not just the question that was asked, albeit in an exam environment. If you're given something like this, you're not going to be asking about the highest, so you don't really worry about this part of the algebra. You don't worry about this math in here. But just to give you more insight of what's going on with it, this is what's going on. So that's the vertical displacement. Obviously, the object was not just going up and down. The object was also drifting toward the east because it had an initial velocity of 6 meters per second. But now we know how long it stayed suspended in the air. It stayed suspended for 6 seconds. For 6 seconds, it was going also in the east direction. So in this case, we want to know when it landed, where it did land exactly, how far is it from the origin? Well, that is not hard to find because on this axis, there is no acceleration, there is no deceleration. The object retained its velocity all along. So by the time it hit this point in here, it was going down with 30 meters per second in the vertical direction, down, not up though. And the 6 meters per second, it stays the same, provided there is no air, or at least the effects of the air are negligible. So in this case, the object continued drifting in this direction. So how much this distance? Well, that's not hard to do in this case. It was just, it was moving with 6 meters per second for every second, but it only lasted for 6 seconds the entire trip. So cancel the second with the second, 6 times 6, it went for 36 meters. So we could answer all kinds of questions about this problem. So let me redraw it now using a pen, a different pen. So this is how the story of the entire projectile in this scenario is. So this is the x-axis, this is the y-axis. So the object went like this. Let's give it a little bit steeper, because that's what it was. And came down. Okay, where did it land? It landed at a distance of 36 meters from where it was launched. So this is the launch in here. Okay, how high did it go? It went as high as 45 meters. That's the highest point that it reached. How long the entire thing took? 6 seconds. The initial velocity was in such a way that this component was 30 meters per second. And this component was 6 meters per second. Okay, so for the entire projectile, this is its motion. I hope this example, this problem actually from the book, that is actually one of the problems that was assigned to you guys, makes more sense to you, albeit this question in here was not part of the question, but it gives you also more details about the entire projectile and how it went and so on and so forth. Okay. There was another question, and I think it's very important to understand. The angle of launch plays a major role, actually. Let me try to draw that. The launch angle plays a major role. So here is the thing. I could throw it at a very small angle, and the object would land not too far. So this is the angle of that I'm going to throw it. If I throw it at 0, it's not going to travel at all. And if I throw... What happened here? If I throw it straight vertical, because if I'm neglecting the air and the effects of the air, it's going to go up and come back. It's not going to drift. If there is no blow, no breeze, no nothing, then it's not going to go anywhere. So it's going to go up and down. So those are the limits, either at 0 degrees, at 0 degree angle, or 90 degree angle. 90 degree angle is going completely vertical. Okay. Okay. Now here is the trick with it. If I throw it at an angle like this, it's going to land in here. If I throw it at the complement of that angle, meaning at an angle that adds up, so this is the angle that let me pick up a different color so that you can see what I'm doing. So this is the angle, the launch angle. Okay. So this is the angle I launched this projectile. Now, if I throw it at an angle so that this angle plus the other angle make 90 degrees, look what happened. So I'm going to throw it at a different angle. So this is the initial launch now, in such a way that this, provided with the same speed too, of course, the speed also plays a role into it. So provided that this angle is the same as this angle. In other words, this whole angle, the new launch now angle, and the initial angle add up to 90 degrees. Then in this case, this is what the projectile will do. It's going to land exactly in the same spot, the same spot as the first one. So it's going to go up and come down. Oops, my hand drawing is kind of lousy on this machine in here. But the point being in here is it's going to land exactly into where the first one landed. Oops, did I draw the whole thing? Yes, I did. Doesn't erase only piece of the path. I hope that you guys see that. This is supposed to be a parabola. The path is supposed to be a parabola. I hope that parabola. Okay, so that's the trick with it. Okay, and that is the idea behind it. I probably will share with you a GeoGebra link down the road. GeoGebra link. where you're going to see this, and you can actually play with the angle, the launch angle, and you will see exactly what I'm talking about in here. And I probably will do that either most likely today, and I'm going to follow up with a message, okay? Concerning how you're going to start to change the angle, the launch angle, and you're going to see that if you do it, for example, at 30 degrees or 60 degrees, it's going to land in the same place. So the range is the same. So the range is the same for complementary angles. What is the complement? So that they add up to 90 degrees. So if I launch it, for example, at 30 degrees or 60 degrees, these two add up to 90 degrees. So in this case, I will have the same range. They will land in the same spot. One of them will go higher than the other, of course. The 60 degrees will go higher, but it's still, they land in the same spot, okay? For example, another 10 degrees and 90 degrees. 80 degrees. They add up to 90 degrees. So if you add up these two, they give you 90. If you add up these two, they give you 90. As a matter of fact, the possibilities are endless. So 25, for example, and 65. Or 15, for example, and 75, and so on and so forth. So all of these angles are the same thing. There is one angle that when you add it, it's going to give you 90 degrees, and you add it to itself. And that angle is 45 degrees. 45 degrees can only be added to itself to give you 90 degrees. This angle is a special angle because it doesn't really have a complement, because it's its own complementary. So that's why it's special in this case, and it has another significance in this case. This is the launch angle to achieve the longest range. Okay, this is the angle where you're going to get the longest range possible, 45 degrees, not any other angle. Okay, the highest point you're going to reach is when you send it at 90 degrees. So basically it goes up and come back in the same spot. Highest is at 90 degrees. So that is the launch that you're going to go with. So that's going to stay the longest and goes the highest in flights. Okay. Obviously, the shortest range is this one too, and the shortest range also is 0 degrees too, because 0 and 90 are also complementary degrees. So they must have the same range. In other words, if this achieves, so if you send it up, it comes back down, it has 0 range. So this one also has 0 range. Okay. So that is some of the properties of the projectile. Now, all of this remarks is when the air is neglected or no air effects. So if you go to a range, for example, try shooting or doing some things in there, you will know that actually the air resistance plays a role too. Okay, and the bullets travel in such a way, for example, that is not exactly as math like this one is, because depending on its speed, of course, because of the humidity in the air resistance, and all of the other effects, and whether or not it's actually spiraling or not, because that also could have an effect. It would usually have an effect. And in the case of sports, for example, also the air resistance plays a major role, whether you're in baseball, soccer, it doesn't matter how you kick the ball. First of all, the geometry of the ball plays a role, for example, in the case of American football, and that's why they give it that spin in there so that it goes spinning, or in soccer, for example, or in basketball, the size, the shape, and all of the things. And for the case of baseball, for example, the kind of threads that it has, so many other things that comes in. What we're talking about in here are point particles, so that all of these effects are neglected. So the shape, the geometry, the texture, and all of that don't come into play for a point. And then no air resistance. So all of these things are, in a sense, idealized cases, okay? So all of these things that I was talking about in here, in the case we're talking about point particle, all of the other effects do not matter really that much, okay? So if you go, for example, in military, and they ask you, for example, to point the cannon toward a specific point and try to get to the maximum range, at that point, you would really be looking for the weather conditions and the temperature and the wind, which direction it's blowing, and so on and so forth. And it's not going to be exactly 45 degrees. As a matter of fact, usually the number is around 39 degrees or something like that. So just because of the air resistance and how it impacts the projectile going up, and then how it impacts coming down, okay? So there is and depending on the size of projectile and so on and so forth. Okay, so I think we covered the projectile enough so that we can do more problems actually down the road and understand actually the problem that we did actually in class together. So I hope that this problem really helps, okay? And as promised, I'm going to make a GeoGebra basically animation. We're going to go there and change basically the angle of launch. And as you've changed the angle of launches, you should be able to see visually, first of all, where it's going to land. And also, you can actually get some numbers there from it too, so that you understand the problem much easier, okay? So that's going to be not an assignment, but it's just going to be an extra activity for you guys to understand what's going on. This is the entire two topics in this chapter. So chapter 4 now is covered. Let me introduce chapter 5. I know it's still next week, okay? And chapter 5 deals with the force of gravity. And the reason why I'm doing that, because it ties into another problem that we did, and namely problem 60. From page 77 still. This we did it also yesterday in class, you guys remember. Is it yesterday? Monday. Yesterday was not Monday. No, I'm sorry, Monday. Now I'm confused with the days too. Yesterday was not Monday. We did it on Monday, okay? Sorry. Anyway, so that problem, you guys remember, gave us the following pieces of data. It says that the moon is at a distance from Earth on average about 3.8. Technically, it's 3.84, okay? Times 10 to the power 8 meters. If you ask anybody, it's 384,000 on average kilometers from Earth. And that's really an average distance. Remember, the path of the planets and the moon in this case is not exactly a circular path. It's slightly, because it's actually an elliptical path. So in other words, twiggle a little. Sometimes it's closer than this number, sometimes it's further. But if it's what's a few thousand here and there, what's 4,000 kilometers versus 384,000 kilometers, it's nothing. Basically, it stays for all practical purposes as circular path, okay? There is a quantity in this case called the eccentricity that people measure to tell you how circular the path is. If that eccentricity turned out to be 0, then in that case, you're dealing with a circle. If it deviates slightly from a 0, then it's slightly off of a circle. And that is the case for the case of the moon. It deviates slightly from the circle. So the point being here is this is the path of the moon. This is the radius, actually. So think about this geometry. So again, that was a problem that we discussed on Monday. So you have the center in here where the Earth is. And the moon is going on a circle. This distance from the Earth to the moon is 384,000 kilometers, or 3.8 times 10 to the power 8 meters, okay? Because a kilometer is 1,000 meters, so it's 384,000 kilometers, or 384 million meters. And million is 10 to the power 6, but then you add 2 decimal points and make this one 10 to the power 8, okay? So that's roughly what this problem is saying. Now, it also says that the moon goes around the Earth in about 27 days. 27 days. Again, I mean, if you look at the astronomy, in astronomy, this number is not correct. It's 27.3 days. Okay, that is really the period, how long the moon takes to go around the Earth. So what does that mean? Because we know the lunar month is about 30 days or 31 days. On average, it's 29.5 days. I mean, you and I, a few days ago, 2-3 days ago, we were in a full moon. If you wait another full moon, it's going to be either exactly 29 days when it's going to be another full moon, or 30 days, one of the two, okay? it's going to be probably a number in between them. On average, if you add all of the numbers year round, you're going to get 29.5 days. So what's going on in here? Is it 29.5 days or is it 30 days? If you took any astronomy class, you will know the distinction between the two. This is the actual rotation. This is the actual number of days. But there is another issue in here. The reason why we account for the extra, because the way usually we count the moon is from a new moon to a new moon, or if you want to, from a full moon to a full moon. As it rotates around the Earth and comes to the next same phase as it was before, the Earth would have moved from its position because it's going around the sun while the moon is going around it. So in this case, it's not going to align perfectly with the sun the way it was aligned before. So you need those extra 2 days to align it correctly. This is what is known as a sidereal lunar month, and that has to do with the actual rotation of the moon around the Earth. So that's not really the point in here. The point in here is a question that was asked from you is just take this for granted for this particular class, and you were supposed to find the acceleration, the centripetal acceleration, where the centripetal acceleration for this purpose is given by the velocity squared divided by the radius. The radius is this exact number. Okay. And this is actually the period, how long it takes to go around it. I don't have a velocity, but the trick that we did, remember, guys, we said, okay, the moon goes on the Earth in one lunar month, which is 27.3 days, around this circle. So you travel this entire circumference. This goes on a circle. And what is the circumference? The circumference is related to the radius in geometry as just 2 pi times the radius r. So this is from plane geometry. So we know the distance traveled. So this is the distance traveled. And this is the time it travels in it. It's 27 days. This is the time, where the velocity in this case is no big deal. It's distance over time, except that the distance is 2 pi times really 3.84. I'm going to write the correct number that I know people usually use, 3.84 times 10 to the power 8 meters divided by 27 days, or 27.3 days. Now, here is a problem. We're not asked to find the velocity in meters per day. We wanted to find how many meters per second, actually. That's what the velocity is. Remember, in the Système International SI, the velocity is in meter per second, not in meter per day. So we need to see how many seconds are in a day. Well, first of all, how many hours in a day? There are 24 hours in a day. And then how many seconds in an hour? Well, we need to know how many minutes, first of all, in an hour. That's 60 minutes in an hour. And then we need to know how many seconds in a minute. Well, that we know, 60 seconds. So the answer now is going to be exactly in meter per second. So we will have the velocity if we do the numbers. So let me do that quickly with you guys in here. I know we did it in class, and I did some approximations and so on and so forth, but I want to really make sure we have the numbers. So let me pull the calculator first. Let me stop sharing and let me share the calculator. Share. Remember, we're doing chapter 5, not chapter 4, okay? So I know this problem is from chapter 4, but I'm introducing chapter 5 using a problem from chapter 4. So again, what we said in here is the distance traveled, which is 2 times pi, here is pi, times the radius, which is 3.84, times, the way this calculator works is you put the exponent first. So times 10 to the power 8. So I'm going to put 8 in here, and I'm going to put 10. So it's 100 million. Okay. So if we put equal, this is a big number. Okay. Forget about the big number. I don't care about it at this point. I just want to find the final answer to the velocity. I'm going to divide this number by open parentheses. Remember, it's 27.3 days. And each day is 24 hours. And each hour is 60 minutes. And each minute is 60 seconds. That will ensure for me to give me the denominator in seconds. Okay. And I put everything in here in calculator. Is giving me 1,022 meters per mile. So I'm going to write that number as 1,022 meters per second, 0.9. Okay. Because I'm eager really trying to find the a close answer from the book, okay? So this actual speed, I know we did in class, we put it 1023, and that's a good number actually, 1022.9 meters, okay? Usually it's not that precise, but I want to really find the correct answer as close as possible from, and tell you the story exactly how we came up with the law of gravity, because chapter 5 deals with the law of gravity, by the way. Gravity. And this is problem is really introduces the law of gravity beautifully. So we know how fast the moon is going around the Earth. That means it's going 1,000 kilometers every second. So in 1 minute, it's going 60 kilometers basically around the Earth. In 1 hour, 3,600 kilometers around the Earth as it moves around. In 1 day, multiply that number by 24 and multiply by 27, by 27.3 is going to complete the entire cycle. So that's how fast the moon is going around the Earth while spinning, okay? Now when we have the velocity, now we need to find, we have the radius. So we're in business, we can find that acceleration. That's exactly what we did in class, if you guys remember. So we take this number that I just found, which is 1022.9 meters, and square this number and divide it by, I'm sorry, meters per second. What am I doing? Meters per second. And divide it by 3.84 times 10 to the power 8 meters. Obviously, I'm going to have a meter squared and second squared in here, and I'm going to cancel one of the meter squared with a meter. I'm going to have the correct unit at the end, meter per second squared. So let's do that now. Let's go back into the calculator, square that number and divide it by 3.84 times 10 to the power 8. So I'm going to stop sharing now to find this acceleration, because that's how the book starts actually. If you look at the, so I'm going to share. So the last number is actually the speed. So I'm going to keep it, okay? So I'm going to square that number by hitting the square in here. So it gave me this big, ridiculous number, which I don't care about the actual v squared. All I have to do is now divide it by the radius. Open parentheses again to be on the safe side. 3.84 times 10 to the power 8. Again, the way this calculator works is I put the power first, and then your calculator may work differently, okay? And then put the power. So this is basically what's going on. Close the parentheses, and now we're in business, and hit the equal sign. So the answer is 0.00272. I'm going to keep 3 sig figs only, okay? 0.0272. So share. The acceleration of the moon turned out to be 0.0. How many zeros? 2. After the decimal points, yeah. Yes, 2 zeros. 272. So there are 3 sig figs in it, because there is a 4 after that. I'm not going to put it rounded up. I'm going to round it down, okay? So that's really what we have found in here. Okay, meter per second squared. That's important. I'm going to do the following, okay? I'm going to take the acceleration on Earth. I mean, an apple. This is an apple falling on Earth. Any object falling on Earth will follow the acceleration g, and that is 9.8 meter per second squared. This Mr. Galileo has found this number. So I'm going to take the ratio of these two accelerations. So I'm going to say the acceleration of the apple on Earth over the acceleration of the moon on Earth also is falling on the moon too with the same acceleration in here. What's preventing it from falling is the force of gravity, that's all, okay? Or actually what's causing it to fall is the force of gravity. So it has an initial velocity, that is why it's not falling. It has this velocity of 1,000 meters per second. That is the one that is preventing it from falling, okay? So what I'm saying in here is this is 9.8 meter per second squared, and this is 0.00272 meter per second squared. I'm going to take the ratio of these two numbers and see what they look like, okay? So I'm going to go back into my calculator. Stop sharing. So I'm going to share the calculator. So what I ended up saying in here is 9.8 divided by 0.00272. And the ratio is 3,600 and some change, okay? And 2, 3,604, if you like, okay? So I'm gonna stop sharing this number and this thing in here. So I'm gonna go back into the calculator and say that the ratio actually is 3,603, because remember it was 2.9. And it has no, this ratio has no units, because this unit of meter per second square and this unit meter per second square, that is, because that's also how much the acceleration of this object is. So the same units, so they cancel out perfectly. So there is no units for this number. It's a dimensionless number, because you have an acceleration over an acceleration, so the ratio is just a full number. So that's the ratio of these two. I'm going to do another ratio here, and I'm going to tell you what that is. The distance from the Earth to the Moon is 384,000 kilometers. Or, yeah, let's write it 384,000 kilometers. It's the same number that we've been using all along. 3.84 times 10 to the power 8 meters. It's the same number. The distance between the Earth and the apple, because an apple is just on the surface. Oops, what happened here? Did you lose everything? Control Z. Control Y. Okay, I lost everything. Anyway, so the distance from the Earth to the apple again is, so let me explain what I was trying to say in here. So an apple is sitting in here, we're dropping it for about 1 meter or 2 meters, or even 10 meters. We drop it from a very high building of 10 meters. I mean, from a typical tree, it's about 2 meters. And 2 meters is nothing compared to the radius of the Earth, which is about 6,400 kilometers, okay? 6,370 kilometers to be more exact. Okay? It's not even, it's roughly this distance, okay? 3,400 kilometers, roughly, okay? So we're gonna put it roughly, because if you add a meter to it, or even if you add 10 meters to it, even if you add a kilometer, you smash it from a tall mountain, okay? So it's still going to be roughly 6,400 kilometers. That's mainly the point I'm trying to make in here. What I'm going to do in here is the distance from the Earth to the Moon divided by the distance from the Earth to the apple. I'm going to find the ratio of these two numbers. So again, this is 384,000 kilometers divided by 6,400 kilometers. And it doesn't matter now, I did not use the meters because both of them are in kilometers, so the kilometer cancels the kilometer. So this is also going to be a ratio of two numbers of the same unit, so it's going to be just a fixed number. So let me go back into the calculator and divide 384,000 by 6,400 kilometers and see what that is. So I'm going to share the calculator again and take 384,000 divided by 6,400, and the answer is 60. The ratio is exactly 60. So I'm going to go back in here and put the answer. And this is also has no units, okay? So the ratio is 60. Remember, it's slightly off. I made an approximation for this 6,400. It could be slightly small change. Here is the key thing. If I take the square root of this number or square the 60, if I square the ratio 60 times 60, well, 0 times 0, that's going to be just 2 zeros in here. 6 times 6 is 36. So this is 3,600. This is almost the same ratio of the accelerations. That is really the kind of the thing that Mr. Newton was facing. This is actually how he made an argument. Let me explain his rationale, and that's we're going to end this one in here based on his rationale. Of course, London in the 1660s was hit by the plague, and he was a student actually in college at that time, and he already came up with 3 laws of Newton, namely the first law, which is just basically a rewrite of Galileo's work for the law of inertia, the second law, which is F equals to ma, and the third law of action reaction principle. At that time, Kepler died a long time ago, actually, and he came up with his 3 laws also that explain the motion of the heavenly bodies in the sky, namely how the planets go around the sun. And it was a beautiful work that everybody was astonished by his laws too, okay? One of the laws he came up with is that every planet, as it orbits the sun, it's this time it takes squared is proportional to the distance, the average distance from the sun cubed. So he came up with 3 laws. That's the 3rd law of Kepler. So actually, when the plague hit London in the 1660s, Mr. Newton was born in 1643. So he was still in his early 20s when this thing happened. And Mr. Galileo died in 1642. There was only like a few months apart between the two, okay? Between the death of one and the birth of the other. So when the plague hit London, he was asked, here are the 3 laws of Kepler's. Can you, with your laws of mechanics that you claim explain everything, can you explain to us how the planets move around the sun? Well, he said, basically, it should. These are the laws that explain everything, so they should be able to explain how the planets go around the sun. And since this is what Mr. Kepler have noticed as far as how the planets go around the sun, the 3 laws that they observe, we should be able to explain them, okay, with these 3 laws. He knew, and everybody knew at that time, there must be a force causing these planets to be held in place with respect to the sun as they go in circles. That's what we were talking about, the centripetal force. So he wanted to find an expression for that centripetal force. That's what he called later on the law of gravity. So he theorized, or he at least imagined, that here is the picture. Forget about the sun and the planets and all of that for a moment. He said, let's focus just on an apple falling on the earth. Okay? And compare that to the moon falling on the earth. If I find an expression for these two, well, I'm in business. So he said that this force that is responsible for the apple falling on the earth, and in the same time responsible for the moon falling on the earth, the only reason why the moon does not actually fall on the earth is because it has that 1,023 meters per second as it's flying through the in its orbit, okay? So now, these 2 accelerations must have, he found them. At that time, the distance the Earth to the moon was known. It was known several centuries before, okay? Anyway, so we know the distance to the moon, we know the distance of the apple to the Earth, which is about 6,400 kilometers. When he did the ratio of the 2, he found the ratio of the acceleration is about the square of the ratio of the distances. So he said that, first of all, this force must be inversely proportional to the square of the distance, because the apple being close from the Earth, its acceleration is 9.8 times meters per second, whereas the acceleration of the moon, which is 384,000 kilometers, is a lot less, 0.0272. And that ratio is the same ratio as of how far the apple is from the Earth versus how far the moon is from the Earth, squared. Okay, which was 60. When you square it, is exactly 3,600. So he said this law must then, the further you are, the less it's going to be by the distance squared. So that's how he reasoned the square of the distance. Then he also reasoned another rationale in this case, in that the force of gravity also must be proportional to the mass. Because if I take an apple, it's going to smash the ground with a certain force. I can measure that force. But if I can take a boulder, for example, and drop it, it's going to do more dent to the ground than an apple. As a matter of fact, I can take the apple and put it on a scale and see how much force is being pulled on. I can put it attached to a spring and basically see how much it's going to pull the spring and measure that force. If I want to, I could do the same thing with a boulder, and the boulder will bring the rock further. So this force must be proportional to the mass. Of course, that's how he argued his F equals to ma to begin with. So for him, the force as for the apple, for example, it's proportional to the mass of the apple. But he said, imagine for a moment that you're a worm, for example, living on the planet Apple itself, okay? So as the apple is falling, you look up in your backward, basically, universe where you are on the apple. So you're actually from the bottom. And here, when you look up, you see the ground, the earth, rushing, coming to meet the apple. So it's actually the earth that is falling on the apple from the vantage point of the worm. So for the worm to make sense to him, then this force must be proportional to the mass of the earth, not the mass of the apple, because he's sitting on the planet apple. So in this case, the apple is the one falling, the earth is the one falling on the apple. And that is actually in compliance with the third law of Newton, which is the action-reaction law. So that is still true. So this force must also be proportional to the mass of the earth, in addition to the mass of the apple. That's how he came up with his law. And he did two things to the law, which we're going to explain next time around. He made it, first of all, so that it's really a force, because as is, it's not a force. Mass squared divided by distance squared is not a force. It needs to be a meter divided by second squared times a kilogram. So it needs to be a mass times a meter divided by second squared to make sense, to become really a force. Okay, that's what MA is. M is a kilogram and A is meter per second squared. So you need this unit to match. The other thing also, we know the acceleration of the earth. On Earth, I'm sorry, the gravity on Earth. So for an apple, we know exactly what the number needs to be, which is 9.8 meter per second squared. So he forced the new force that he invented to be compliant with what we know, with the experiments of Mr. Galileo at that time. And that gave him an expression for how the apple falls on the earth and how the moon falls on the earth. And now he said, I'm ready to move on to the planets. As a matter of fact, I'm ready to move on to anything you throw at me. You want me to describe black holes? At that time, black holes were not known, by the way. Or neutron stars? At that time, they were not known either. But I can tell you, he said, anybody in the universe out there must obey this law. And that is why it's named the universal law of gravity. Because he took that kind of analysis for an apple versus the moon, and he made it so that it is applicable for everything out there in the universe. Okay. So this is this whole argument in here. I know some of the stuff that you might read in the books and somewhere else, especially in this weird environment that we're in. We have a lot of this people click and bait on YouTube and everywhere else, where people claim things that are not true, such as an apple falling on his head. And from there, he basically came up with a law. That doesn't make sense. So this is most likely what the story is. Again, this is not directly from him. This is related from his acquaintances, basically, that they say this is how he argued for it. He was not meant to basically talk a lot. And at the end, he published his work in the book called the Principia of what is mathematics, or some mathematical Principia or something like that. And that was 4 years later. He didn't publish it initially because he was struggling with the distance of 6,400 kilometers and how to justify that for the case of the apple. And for that, he really had to do some other things. He had to use a not known subject at that time, namely a math tool called calculus, and that's how he came up with his work. Anyway, I think we went a little bit more in depth into chapter 5 than I really honestly wanted to, but next time around, we're going to revisit some of these points and also build on it and give the actual expression for the force of gravity and discuss it in the context of chapter 5. Okay, thank you guys, and I'll see you guys next week. Stop the recording.